Bismillahirrahmanirrahim. Today we will talk about the chapter 3 in the book Concise Introduction to Pure Mathematics, and we'll talk about the decimals. So previously we have talked about the reals and then number systems, rationals and irrationals. Now we will talk about how we represent a number in decimals. So it is all very well to have the real number system as points on the real line, but it is hard to prove any interesting facts about the reals without any convenient notation for them. So we don't have any notation for the reals. We now remedy this by introducing the decimal notation for reals and demonstrating a few of its basic properties. We are familiar with the following decimal expressions that let's say we know that 1/2 is 0.5, but we can also write this is, we know that 1/9 is 0.1111, so on. We know that 1/7 is 0.142857142,857, and so on. Now, but what do we know mean when we write, for example, 1/9 is this? We mean that the sum to infinity of the series. So when we write this, we mean that the sum to infinity, so of the series. Which series? So 0.111 dash means 0.1 plus 0.01 plus 0.001 plus and so on is nothing but 1/10 plus 1/100, or you can write 10 square plus 1/10 cube is like this. And this is, so if the sum to infinity of above series is 1/9, and we can get as close as we like to 1/9 provided we sum enough terms of the series. Yeah, to make this absolutely precise would require us to go into the concept of limits and convergence, which we shall do much in later chapter 23. For now, I hope the meaning is reasonably clear. Okay. The above fact about 1/9 is a special case of the following result on geometric series, which is probably very familiar. So let's state that. We have a proposition 3.1, which says, let x be a real number number 1 if x is not 1, then sum of x square plus x cube up to x power n is equal to x into 1 minus x power n divided by 1 minus x. Okay. Number 2 is, if -1 is less than x is less than 1, then the sum to infinity of x squares of x is nothing but x over 1 minus x. Perfect. And we can prove this. So we can give a proof for this. So let's prove part 1, which says that let Sn is the series of squares of x up to n terms then xsn will be the series, which is x square plus x cube x power 4 up to x power n plus 1. Now subtracting, we get subtracting we get 1 minus x into Sn is x minus x power n plus 1, which gives 1. Because we can write Sn is x minus x power n plus 1 divided by 1 minus x. Or you can still write x into 1 minus x power n divided by 1 minus x. Okay, now part 2 is we know since minus x is between minus 1 and 1, we can make x power n as small as we like, provided we take n large enough. So we can make x power n is small as we like, provided we take n large enough. So we can take the sum in 1 as close as we like to x over 1 minus x, provided we sum enough terms. So you are saying this is to say the sum to infinity is x over n. So you can say, so we can make the sum Sn x into 1 minus x power n over 1 minus x is close as we like to x over 1 minus x, provided we sum enough terms. Okay, this is to say that the sum to infinity is, so the sum to infinity of Sn, which is x into 1 minus x power n over 1 minus x, is x over 1 minus x. And this proves true. Now, we can write, so let's write x is equals to 1 over 10 in the proposition given above. So let's write x is 1 over 10 and the proposition gives. Then by proposition 3.1, we get what? Get 1 over 10 plus 1 over 10 square plus 1 over 10 cube plus this sum into infinity is, what is x? 1 over 10. What is 1 over 1 minus x? 1 minus 1 over 10. If you solve this, you'll get 10 minus 9 over 10. And you can write 1 over 10 multiply, sorry, this is 1 not, multiply 10 over 9, and this is 1 over 9. So sum up to infinity is 1 over 9 of this series. Likewise, in general, the decimal expression. So in general, the decimal expression, which is expression, this expression, a naught point, a1, a2, a3, so on, where a naught is an integer, and a1, a2, a3 are integers between 0 and 9, means the real number that is the sum to infinity of the series a naught plus a1 over 10 plus a2 over 10 square plus a3 over 10 cube plus so on. With this understanding, we obtain the next result. We obtain the next result, which give us the convenient decimal notation for all the real numbers. So we can write proposition 3.2 says that every real number x has a decimal expression, that is x is a0 point a1 a2 a3 so on. And we can prove this point by saying that now we can picture x on the real line. So let's say this is real line, and here is x. And we know that x lies between two consecutive integers, let's say let a0 be the lowest of these, so that we can write what? We can write a0 is less than x or equal to x, and x is less than a0 plus 1. So we are saying we have a0 plus 1 here, and we have a0 here. Maybe it's not even here at x. Now divide the line between a0 and a1 into 10 equal sections. So now we have a line. Now we have a line, and we have a0 here, a0 plus 1 here, and x here somewhere. Now we will make 10 sections of this line. So divide the line between a0 and 10 equal sections. So 10 equal sections. Certainly x lies in one of these sections. X lies in one of these sections. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, so we can find a1 between 0 and 9 such that x lies between one of these sections. So we can find a1 between 0 and 9 such that we can write a0 plus a1 over 10 is less than or equal to x. X is less than or equal to a0 plus a1 plus 1 over 10. Okay. Similarly, we can find a2. a2 such that a0 plus a1 over 10 plus a2 over 10 is less than or equal to x. X is less than a naught plus a1 over 10 plus a2 plus 1 over 10, and so on. And so on. Now, if we do this enough times, the sum to a naught plus a1 over 10 plus a2, so this should be square, this should be square, a2 over 10 square gives what? Gives this gets is close to as close as we like to x. To explain about this is what we mean by x is. So we can write x as a naught point, a1, a2, a3, so on. So every real number x have this kind of expression. Now let's try to imply this proposition and apply this proposition on some example. So let's say we have under root 2 can be written as a naught point a1, a2, a3. Now we will use the process of the proof which we used in our proposition. We do that. So observe that. First, observe that 1 square is 1, 2 square is 4. So under root 2 lies between 1 and 4. Sorry, 1 and 2. And hence, we know that a naught is going to be 1. Next, 1.4 square is 1.96, while 1.5 square is 2.25. So a1 is 4. a1 is 4. Likewise, 1.41 square is less than 2, while 1.42 square is greater than 2. So a2 is 1. We can continue finding decimal digits in this way until we get really fed up. And you can show that under root 2 is now 1.41, so on. Perfect. Now, we have a convenient notation for all the real numbers. They all have decimal expressions. Two basic questions about this notation arise immediately. Can the same real number have two different decimal expressions? And if so, can we describe exactly when this happened? Question number 2. Which decimal expression are rational and which are irrational? So let's say, let's write these questions. Question 1. Can the same real number have two different decimal expressions? And if so, can we describe exactly when this happened? Number 2, which decimal exactly describe rational and irrational? Okay. Now we shall answer these questions in a few results. For one, number 1, notice that 0.9999 goes on, can be written as 9 over 10 plus 9 over 10 square plus 9 over 10 cube, and so on. And we can all still write it 9 into 1 over 10 plus 1 over 10 square plus 1 over 10 cube plus so on. And this is nothing but 9. You know, this will go to 1 over 9, and this is nothing but 1. Interesting. So this expression, if it goes to infinity, will equals to 1. Okay. Thus, the real number 1 has two different decimal expressions. Which one? So 1 can also be written as 1.0000, and this can also be written as 0.9999, and so on. Similarly, for example, so this is we are doing for 1. Similarly, you can write 0.25799, so on, is 0.258000, so on, and 1299.9999, so on, is also 1300.000, so on, and so on. We can write so many. So in this way, only way two different decimal expression can be equal. Is this the only way? Is this the only way? Yes. The answer is yes. This is the only way. This is the only way two decimal expressions are equal. Perfect. And we can give the proposition for this. 3.3. It says that suppose that A naught, A1, A2, A3, so on, and B naught, B1, B2, B3, and so on are two different decimals expressions for the same real number, then one of these expressions ends in 9999, so on, and other ends in 0000, and so on. Perfect. Now, there we will end the first part, like this lecture, and in the next lecture, we will talk about the other expressions and things. And then we will talk about the question number 2. Okay.